Okay, so this is a continuation of section 8.3. And in this lecture, we're going to show that actually the existence of primitive roots for parts of primes. Remember that in previous lecture, we did show that the existence of primitive roots for square, p squared, for any odd prime p. So now we're going to generalize this to higher powers of the primes, bigger than 2. All right. So again, we're going to get started with a lemma. This is the second lemma for this section. We're going to put it lemma 2. Again, in here we're going to let P be an odd prime. And we're going to take a primitive root. And we're going to let R be a primitive root of P. That satisfy this condition such that R to the P minus 1 is congruent to, is not congruent basically to 1 mod P squared. But in fact, this is also equivalent, this congruent to saying that R to the P of P, all right, is not congruent to 1 mod P squared. Then for every k bigger than or equal to 2, we have also this non-congruence relation is satisfied. Phi of P to the k, actually k minus 1. All right, this one is not congruent to 1 on P to the k. All right. Again, this is equivalent in terms of. And I switch things around in here. So this one is R to the phi pk minus 1 is pk minus 2 times p minus 1. And this is not congruent to 1 on p. All right, so some sort of similarity between the two, and we use this one actually to show that R or R plus P is a primitive root for P squared. So we're going to use this to show that actually the same thing is true for P to the k, for any k bigger than or equal. All right, the proof of this is by induction. Of course, on k. So the base value is for k equal to 2. The congruence that we are interested in, or non-congruence we are interested in, is this. R, I'm going to use this, which is the easier one for this case. So when we have 2 minus 2 times p minus 1, all right, is, oops, wrong one, we need the power. All right, this is R to the p, so it's going to be to the power 0, and then we have p minus 1 is equal to first R to the p minus 1, and I know this by hypothesis, this is not congruent to 1 mod p squared, because k is squared. So this is holds by the hypothesis. All put the inductive step, and we're going to assume that the statement holds for k bigger than or equal, for some k bigger than or equal to. Let's assume that r to the power p to the power k minus 2, p minus 1, that's not congruent to 1 mod p to the k for some k bigger than or equal. All right, now remember that we have greatest common divisor of r and p is equal to 1. And if we have shown that I can take any power for both r or p or one of them, and still they will be relatively prime. So in particular, I want to do this r to the p to the power k minus 1 is the same as also r p to the k is equal. Well, now we're going to apply Euler's theorem. So by Euler's theorem, since all these relatively prime relation holds, I can do this one for p to the power k minus 1. All right, and this is congruent to 1 mod p to the k minus 1. And of course, this is equivalent to r to the p k minus 2, p minus 1 is congruent to 1 mod p to the k minus 1. Remember, we're interested in showing that this is not congruent to mod p to the k. So this one is k minus 1, actually the equivalence relation holds. All right, what does this here imply? This means that we can write r to the p to the k minus 2, p minus 1 is equal to 1 plus a p to the k minus 1. Because it divides, and when I change the divisibility relation into equality, we get this for some integer k. Integer a. Well, we're going to take this relation or this equality and raise it to the pth power. Okay, so we're going to take the pth power of both sides. So we're going to raise both sides of this. To the pth power. So what we get, of course, r to the power p k minus 2 p minus 1 p, and this is equal to 1 plus a p to the k minus 1. And there are some similarities in the proofs, and then of course we're going to this is the pth power. So we're going to use the binomial theorem to expand the right-hand side. So first, the left-hand side becomes r. The p here, it's going to make this is p to the k minus 1, and this is p minus 1. Well, we're going to show that the statement, or the incongruence holds for k plus 1. So it's kind of unusual the way we're going about this, but eventually that's what we will get. All right? Now, by the binomial theorem, we're going to get 1 plus b1, and then a, b, k minus 1. We're going to have a square in here, and this becomes x to the minus 2. All right? No, actually, first we need just a. All right? And this is b minus 1. So 1, and then this, then b 2a squared, b minus 2, and b minus 1 quantity squared, and so on. And the last term is going to be b, and a or b k minus 1 to the. All right. Let's work on these binomial coefficients and see how do they simplify to. So this is equal to 1. This one is going to be b factorial over b minus 1 factorial a b k minus 1 plus. Let's be like this also, b factorial over 2 factorial b minus 2 factorial. And then we have a squared, and then b2k minus 2, and then the other terms. And the last actually binomial coefficient is 1, so this becomes to the b, and leave it as is. All right, so this is equal to 1 plus a b to the k, b minus 1 factorial cancel out, so we end up with a b. So you get this, and in the plus, the other term is going to be actually b minus 1 over 2, and we get the p out of this, so we come up with this is a squared b to the 2k minus 1 and 4 out. Now eventually we're going to be taking this mod b to the power k plus 1. So we have all of these, they actually have b k plus 1 factors. Right, so this is 2k plus 2k minus 1, so you can write it as k plus 1 and adjust for the other to make it 2k minus 1 and so on. So when we do the congruence in here, so this becomes congruent to 1 plus a b to the k mod dk. But we really need to get to k plus 1. Now I claim that this term right here is not congruent to 0 mod b to the k plus 1, which make that this one is not congruent to 1 mod 1. All right? So let's do that. So we have, for set p does not divide a, all right? And also we have this. This is actually, this implies, so this is equivalent to saying that a is not congruent to 0 mod p, all right? And this itself also implies that one other thing also we have b to the k is not congruent to 0 mod b k minus plus 1. That's it. All right. So now these together implies if I multiply them, this is not going to congruent to 0 mod b to the k. All right. Therefore, our conclusion is r to the power of b to the k, actually k minus 1, b minus 1 cannot be congruent to 1 mod. Actually, let me say it is congruent to this 1 plus a b to the k, and this is not congruent to 1 mod b to the k. So by math induction, then we have the statement is induction. This implies the congruence. It's not congruence actually, not congruence, but let me write what it is. It's b to the k minus 1, b minus 1 is not congruent to 1 mod b tables. And now this is the proof for every k bigger than or equal to 2. All right. Now we are ready to show that p to the power k actually does have primitive root for every k bigger than or equal to 2. Right, this is theorem 8.9, I think. Yeah, so if E is an odd prime, and then p to the k has a primitive root or any k bigger than or equal to 1. Of course, for the cases k equal 1 and k squared, we already proved these, so we're interested basically in the case for k bigger than or equal to 2. All right? But just to make it as a statement, this is what we want to actually make general. All right, so let's recall that the two lemmas that we're going to be using in here and what they tell us. First, by lemma 1, we have shown this. We know that p has a primitive root r, which satisfies this. That is also a primitive root of p squared. That is also a primitive root of p squared and satisfy the congruence to satisfy this condition. R to the p minus 1 is not congruent to 1 mod p squared. Now, lemma 2 tell us also, we also have R to the p k minus 1, p minus 1 is not congruent to 1 mod p to the k. All right? We're going to be referring back to this. So I put a star in here later on in the proof. All right, now we claim that R, this same R, actually is a primitive root of p to the k for every k, bigger than or equal to 1. But we already know it is actually primitive root of p, and we also have it for 2p squared, so we're just going to do it for bigger than or equal to 2. Well, so let me put the claim. That it is in that R is the primitive root of p to the k for every k bigger than. So let's assume actually M is the order of R mod p to the k. So our objective is to show here, need to show M is equal phi p to the k. So which make it into a primitive root. Well, let's see what does this M equal to the order. Then we know that M divides phi of p to the k. The order is the smallest exponent to make the congruence congruent to 1. So in here we have this, implies that M divides p to the k. All right, also, which is equal to p k minus 1. All right, also in the also this one is what we're saying, that R to the M is congruent to 1 mod p to the k. Also, this holds by definition of order. Now, since p is a divisor of p to the k, then the congruence relation holds this, R to the n is congruent to 1 mod p, because it holds for any divisor of the modules. All right. Now, also we know that R is a primitive root. P. This implies that the order, of course, order mod p of R is equal to p minus 1, which is equal to phi of p. And then we have also this divisibility, all right? have this. All right, and the order in here, both of these implies that p minus 1, which is the order, is going to divide m. All right? And that in itself implies that m, so this relation p minus 1 divides m implies m equal q times p minus 1 for some q. All right, now let's look at the another divisibility. Basically, here we have the m. Actually, also this one divides phi of p to the k, and this is p minus 1 and p minus 1. All right. Again, this tells us that when in terms of m, this means q. I substitute for m. All right, I substitute for m by q p minus 1 divides p to the power k minus 1 p minus. And this also implies, by canceling out p minus 1, so this implies q divides pk minus. And this makes q is equal p to the t for some exponent t could be 0, as low as 0, and the highest is can be k minus. This is the highest exponent of the p. All right, and with this, therefore, the m is going to equal p to the t times p minus. Well, I'm going to show that, in fact, t must equal to, okay, so this is our goal, to show p actually must be the highest exponent, k minus. Well, let's assume it is not. So we're going to do this by contradiction. So let's assume it is not equal, so it's going to be less than that. So let's assume that t does not equal to k minus 1. So this implies that t is going to be less than or equal to k minus 1. All right. Now, what does this mean? This means that the m, which is equal p to the t minus 1, is going to divide, all right, p k minus 2 t minus. Because this one is less than or equal to k minus 2, so the worst can be is if it is k minus 2 or less. So this divisibility relation actually does hold. And remember that this implies, and let me write this as also phi. So this is phi to the k. All right. And actually, this is phi to the k minus 1. All right. So this implies that phi to the power pk minus 1 is equal ml for some integer l. All right. Now, consider this r to the power phi of pk minus 1. So this is equal to r to the power ml, and this one is congruent to r m to the l, and then we're going to do this is congruent p to the k. So r to the m is congruent to 1 mod p to the k, and of course we get that this is congruent to 1 mod p to the k. But actually this contradicts the choice of r and the equation or the incongruent relation is thought. All right. So what does this mean? This means that therefore t cannot be less than or equal. So t is not less than or equal to k minus 2, and it makes the t actually, well, it cannot be equal to 0, of course, so it's going to be actually equal k minus 1. And what does this mean? This means the m, which is the order of, so this implies m, which is the order p to the k of r, is in fact equal p to the k minus 1, that's p to the k times p minus 1, and this is equal phi of p to the k. So therefore r is a primitive root of all right. Next, we're going to show that multiples of p to the k by 2 is also have primitive roots. And this is part of the Gauss theorem, which tells us which integers have primitive roots. All right, so this is the corollary. Any integer of the form 2 p to the k, where p is an odd prime, and k is an integer bigger than or equal to 1. So any integer has a primitive all right. This actually does need some argument to prove. doesn't follow just immediately from the theorem, but we will be using the theorem. So again, let's just start with let R be a primitive root, which we know it doesn't exist now, of e to the k. We're going to do, without loss of generality, assume that R is odd. All right? Because because if R is even, then R prime, which is equal R plus P, is odd and is a primitive root, as we have seen, of P to the K, the primitive root of P to the K. But we're just going to restrict ourselves that R is odd. So with this, you can assume the order of R with respect or with mod 2 to the 4 k. We see we want to denote this by 10. Okay, so we're going to let n equal the order 2p to the k of R. All right, so this, of course, implies that n divides the highest power that makes R congruent to 1 mod 2 to the power 2p. So this. Now this one is equal because 2 and p are relatively prime and p is multiplicative. P to the k. And phi of 2 is equal to 1 times p to the k. In other words, we have this divisibility relation, which we will come back to it. So n divides phi p to the k. Our goal is to show actually that n is equal to this. Okay, need to show n is equal because phi of the modulus is equal the phi of e to the k. So if I can show this one, then it becomes n. Actually, it is or R becomes a primitive root. And to do this, to show this, we want to show that phi p to the k is divided set. So these two divisibility implies that n is equal phi p to the k. And to do this, again, let's look at n being the order. Implies that R to the n is congruent to 1 mod 2p to the k. And since R is odd, then the greatest common divisor with 2 is equal to 1. And then I can actually divide by 2 to this congruent. So this becomes R to the n is congruent to 1 mod e to the k. All right. So now another divisor of this, and since it's relatively prime to R, then we can actually, this relation does hold. All right, and this means that we have the order also of b to the k of R is equal t2, because it's a primitive root, t to the k, and this is equal bk minus 1, t minus. And this implies one other thing in here. Actually, I don't need this. Okay. So we have R to the n to satisfy this. And the order of this, because it's a primitive root, is equal to this. Then this implies that the, which is the smallest, this one must divide n. All right? Because the order must divide any exponent that make this is congruent to 1. Now these two, this one and this one, implies that n is equal to p to the k, which is equal to p to the k. Therefore, R is a primitive root. A primitive root of 2p to the k. All right. Now, we have shown basically which number they have primitive roots, which number they don't have primitive roots. And now we need to put it all together, just to remind ourselves of the different pieces that we have shown in terms and forms of lemmas, corollaries, and theorems, and state the main theorem, Gauss's theorem 8.10. All right? When we do this, we'll call it putting everything together. And this is theorem 8. All right. An integer n, and this is called Gauss's theorem, is the reminder again. All right. Any integer n bigger than 1 has a primitive root if and only if n equal to 4 p to the k to p to the k. All right, where p is an order prime and k bigger than or equal to 1, an integer bigger than or equal to 2. All right, let's look at that. So it's really not a proof, it's more of stating the different pieces that we have used to give us list of those. So by theorem, the last theorem which we have, 8.9, and its corollary, to the k or 2b to the k. You know, b to the k is given in the theorem, 2b to the k is given in the corollary, or 2b to the k. So by these as a primitive root. So we are left from this list with 2 and 3. For 2, n equal 2 has r equal 1 as a primitive root. This is not, of course, hard to see because we had, if r is relatively prime to 2, then by Euler's theorem, we have r to the phi of 2 is congruent to 1 mod 2. But phi of 2 is equal to 1, and this is it. All right, so this takes care of 2. Now 4, it turns out that 3 is a primitive root of 4. So for n equal 4, again we have by Euler's theorem, r to the power phi of 4 is congruent to 1 mod 4. R is relatively prime to 4, but phi of 4, the number that are relatively prime to 4 is 1 and the 3. So this means, let me see here. Oh, yeah. So actually, this one is phi of 4 is equal to 1 integer that are relatively prime to 4, 1 and the 3. All right, actually is equal to 2. So this one is mod. Just a minute, we need to see which one actually this does hold for. All right, so this congruence actually does hold for 1, all right. For 2, it doesn't, becomes 4 squared, 2 squared is 4. And of course, which we have r equal to 3. Okay, so it holds for this. So r equal to 3, its order is of 3 is equal to 2. All right, and it make it it's a primitive. Now the other integers of the other types or other forms of integers, they don't have primitive roots. And if we look at what are these. By theorem 8.6, we know that any power of 2 is not other, bigger than or equal to 3. All right. So this one, you just see this. All right. So theorems 8.7 and 8.8. That shows that any integer of a form other than the one listed or those listed in Theorem 8.10 does not have imperative roots. And remember, these are 2 to the k for every k bigger than or equal to 3. And also we have the corollary to tell us also. Then we have this, where m n bigger than 2, and these are relatively prime. So any product of this in them is would take for all of the other numbers. So any number that has actually more than 2 other primes or 2 distinct other primes is going to be have no primitive roots and then all other possibilities. Okay. All right. So this ends actually the list of those numbers which they do have. It's, as I say, very limited. And in the next section, we're going to look at one of the applications of integers having primitive roots. We're going to talk about indices, or the index of an integer or an integer, the index of an integer modulo another integer, and use that to solve a variety of congruence equations. All right, let's start writing.